pH is now going to be equal to 4.9047, which is approximately 4.90. So the pH of 5% weight per volume oxycodone hydrochloride is determined to be 4.90. So these are basically the kind of calculations you find in the case of strong acid and a weak base. Alright, so looking at the case 2, which is a state or a case of a strong acid in a weak base, we are having two questions here we have to look at. And then when we solve these questions, you will see how to be able to attack situations like this. And we have already notified you that basically that once you have a strong acid and a weak base, the pH will be less than 7. Lesser, that is more acidic because of the effect of the strong acid. All right, so let us now look at how we can be able to solve this effectively. So let's see how we can be able to solve this effectively. So question number 1 says calculate the pH of 0.05 mole per dm cube ammonium chloride with a pKa of 9.25. Now ammonium chloride, NH4Cl. Ammonium chloride comes from two things. Ammonium chloride is coming from NH4OH, that is ammonium hydroxide, and HCl. NH4OH and ammonium hydroxide and then HCl. HCl is a strong acid, and then ammonium hydroxide is a weak base. So it fits into the context that we are dealing with. And I remember telling you very clearly that anions of strong acid and cations or strong bases do not like affect the pH in solutions. I hope that makes sense to you. So the pH remains at 7 because these guys do not change or cause any significant change in the pH. So how is sodium ammonium chloride going to undergo hydrolysis in solution? So we have NH4OH is going to dissociate. It's going to dissociate into NH4 plus this is Cl. NH4Cl, that's the salt. So it's going to dissociate to this and Cl minus. So because this is not causing a change in pH, it is not something so significant to us. So we now bring the NH4 plus. I told you that you can do either the NH4 plus straight or you can do it together with water. Any which one you work with is fine. For this case, you're just going to do it straight. If you do it with water, you have hydrozonium ion. And if you do it straight, you just have hydrogen ion. So this will now dissociate into H plus NH3, no plus here. So this H plus is going to be higher in solution, and by implication the pH is going to be lesser. Higher hydrogen concentration, lesser pH, meaning it is going to become more acidic. So how do we solve for this? We already know that our pH is equal to 1/2 pKa minus log C. So our pH is what we're calculating for. pKa has been given to us as 9.25, and then our C has been given to us as 0.05 mole per dm cube. Remember, it must always be in mole per dm cube, and if it is not in mole per dm cube, you already know how to convert it by looking at the previous videos. So we have pH is now equal to 1/2, and then we have our pKa as 9.25 minus log 0.05. So we now have that our pH is now equal to 1/2 9.25. So if we do log 0.05, we are going to have minus in brackets minus 1.3010. So in mathematics, minus times minus is going to give us plus. So our pH is now equal to 1/2 brackets 9.25 plus 1.3010. So if we do 9.25 plus 1.3010, we're going to have 10.55, and then we now divide by 2. That's going to be equal to 1/2 bracket 10.551. So we're now going to divide that by 2, and then we have that our pH is now equal to 5.2755 which is approximately 5.28. So it simply means that the pH of 0.05 mole per dm cube ammonium chloride is 5.28. That is less than 7, which shows that it's coming from a strong acid and a weak base. So when you have situations like this and you calculate and your pH is higher than 7, you just know that there should be a problem somewhere, and it is something you can easily fix by looking at your solving to be sure that you followed it all. Hello, are you tired of feeling lost in class when chemistry is being taught to you in pharmaceutical inorganic chemistry? I'm talking about PCH 231. Come close. I want to show you how that PCH 231 launch by AcademyX.co is happening very soon. Click the description below to see when the course is going to be released. AcademyX is already out to ensure that they help 100 students to ace PCH 231 in one sitting, and it is very important that you book your slot on time so that you will not be left out. So take your time, purchase the course, and then we move on from there to ensure that everybody pass PCH 231 without the hurdle of feeling lost and tired in class while learning. So the second one we are looking at is to calculate the pH of 5% weight per volume oxycodone hydrochloride. Now, oxycodone hydrochloride in this case is a counter ion. I already told you what counter ions are used for, and if you don't know what it is used for, refer to previous videos. It has been explained very clearly. So hydrochloride, but just for context, hydrochloride is a counter ion to help in increasing the solubility of oxycodone as a salt. So if oxycodone is having a counter ion as hydrochloride, it simply means that oxycodone is basic in nature. I hope that makes sense to you. So oxycodone hydrochloride, base and acid, hydrochloride, acid, oxycodone. Yes, that's the idea. So hydrochloride, like we already know, HCl is a strong acid, but oxycodone is organic, and because it's organic, the basicity, like the basic nature, is actually weak. So you have a strong acid and a weak base. It means that this particular formula will yet apply. So we have 5% weight per volume. We have to convert that to mole per dm cube. So let us go all in and begin to solve that. So for oxycodone, in the resource material you have, you see the structure of oxycodone. So for oxycodone hydrochloride, our pH is equal to 1 over 2 pKa minus log C. We know our pKa to be 8.9. What we need is our C. So our concentration is 5% weight per volume. And 5% weight per volume simply means 5 gram in 100 mil. And our drill is, if 5 gram is in 100 mil, S gram will be in 1000 mil. Why 1000 mil? Because like we have established already, we already know that 1000 mil is equal to 1 dm cube. So what I'm simply saying is S gram in 1 dm cube. That's our 1000 mil. And as you already know, how we do it is this times this divided by this by this. I reason as you already know because in the previous videos you have seen me take my time to explain this. So we have 5 times 1000 divided by 100. So we have our x is equal to 5 times 1000 divided by 100, and that is going to give us 50 gram per dm cube. But we're still not there. What we need is mole per dm cube. All right, so for us to convert to mole per dm cube, we're already given the formula. That concentration in mole per dm cube is equal to concentration in gram per dm cube divided by molar mass, which is in gram per mole. So do we have concentration in gram per dm cube? Yes, we have that. Do we have the molar mass? We have been given the molar mass to be 405.9. So we can now calculate that the concentration in mole per dm cube is now equal to 50 divided by 405.9. So we simply do our 50, 50 divided by 405.9. And if we do that very carefully, that's going to be 0. 0.1232 1232 mole per dm cube. So we have 0.1232 mole per dm cube. So can we now calculate for our pH? Yes, we can calculate for our pH. Remember the P is small letter p. So we have pH equal to 1/2 brackets. Our pKa is 8.9, 8.9 minus log our C is 0.1232, and then we now do our calculation. Log 0.1232, we've gotten our answer for that. So our pH is equal to 1/2 brackets 8.9 minus bracket minus 0.9094, and we already established that minus times minus is plus. So we now have that our pH is equal to 1/2 bracket 8.9 plus 0.9094. So what we do there is now going to be 8.9 plus 0.9094, and that's going to be equal to 1/2 bracket 9.8094. So we simply divide 9.8094 by 2. So what we do that, our pH is now going to be equal to 4.9047, which is approximately 4.90. So the pH of 5% weight per volume oxycodone hydrochloride is determined to be 4.90. So these are basically the kind of calculations you find in the case of strong acid and a weak base upon hydrolysis in water. So we're going to be looking at other cases that we have and then move on to buffers from here.